4.2 light-years from our planet, the red dwarf Proxima Centauri currently emits energy equivalent to 600 billion nuclear bombs exploding every second. Orbiting this celestial beacon is a heavenly body that is presumably capable of sustaining living organisms, making it our closest potentially habitable neighbor in the boundless universe. However, a colossal chasm lies between us and this distant world, one that will demand solutions defying the fundamental laws of physics, economic realities, and even human psychology. We must navigate radiation storms capable of melting steel, encounter cosmic dust particles hurtling at speeds sufficient to vaporize entire cities, and contend with energy demands that make our civilization's entire power output seem like a flickering candle. Prepare yourselves. We begin this immersion. Proxima Centauri is perceived as close because astronomers designate it as our nearest stellar neighbor. Scientists often refer to it as the house next door, or a quick stroll down the cosmic street. Yet, this seemingly friendly language masks a terrifying truth that becomes evident once one attempts to grasp the true scale of the distance. 4.2 light-years means that light itself, the fastest substance in the entire universe, takes over 4 years to travel from Proxima to our Earth. Light moves at 670 million miles per hour, fast enough to circle our planet 7 times in just 1 second. Nevertheless, even at this unimaginable speed, photons emitted by Proxima spend over 1,500 days hurtling through the bottomless void before reaching our eyes. Consider this distance from a different perspective. If our Earth were a marble located in New York City, Proxima Centauri would be another marble placed somewhere in the middle of the vast Pacific Ocean. The space stretching between them is absolutely empty. There is no air, no islands, no intermediate stops. Just a black vacuum extending beyond human comprehension, only occasionally interrupted by minuscule specks of dust moving so fast they can punch holes even in solid steel. The fastest spacecraft from the United States National Aeronautics and Space Administration, named New Horizons, is hurtling through space at 36,000 miles per hour. This probe reached Pluto in 9 years, a journey that made global headlines. At this record-breaking speed, New Horizons would still take 78,000 years to reach Proxima Centauri. This time frame spans the entire history of human civilization many times over. Every rocket we have ever built, every speed record we have ever set, every technological breakthrough we have achieved, all of it combined would still leave us crawling like ants across a distance that even light finds challenging. The gap between us and our nearest stellar neighbor contains enough empty space to swallow 1 million solar systems without them even touching each other. However, this astonishing scale represents only the starting point of our challenges. Distance alone would merely be an inconvenience if space were truly empty, a kind of peaceful highway where spacecraft could drift unimpeded for millennia. What lurks within that seemingly empty darkness transforms a difficult journey into a deadly challenge that will test the very limits of human engineering and endurance. 4 light-years sounds manageable until you translate it into numbers that the human mind can truly process. This distance equals 25 trillion miles. A number so vast it requires a 1 followed by 13 zeros to write. If you counted 1 number per second without stopping to eat, sleep, or breathe, reaching 25 trillion would take you 800,000 years. Imagine trying to cover this distance on foot. At an average speed of 3 miles per hour, the journey would require 9 trillion hours of continuous walking. This equates to over 1 billion years of non-stop trekking, a period exceeding the duration of complex life on Earth. You would witness the rise and fall of entire species, the birth and death of mountain ranges, and the slow dance of continents across our planet's surface. Even everyday car travel becomes utterly absurd on such truly grand scales. Imagine a vehicle moving at a typical cruising speed. It would take at least 350 million years to reach Proxima Centauri. During this incredibly prolonged journey, a hypothetical driver would witness our sun complete 1.5 full orbits around the center of our own galaxy. In that time, dinosaurs would have evolved, established their dominance on Earth, and vanished twice, all while you, figuratively speaking, held the steering wheel. The fastest currently existing commercial airliner can reach speeds of up to 600 miles per hour. At this seemingly impressive speed, a flight to Proxima Centauri would take 4.7 million years. Considering that modern humans have only existed on the planet for 300,000 years, this hypothetical flight would last 15 times longer than the entire history of our species on Earth. The pilot, if they could exist for so long, would have to account for numerous ice ages, the development of agriculture, the rise and fall of countless civilizations, and even the very genesis and evolution of space travel. These comparisons graphically demonstrate why astronomers prefer to measure cosmic distances in light years rather than familiar miles or kilometers. Ordinary units of measurement become utterly meaningless when attempting to describe spaces so immense that light, capable of circling Earth in just 1/7 of a second, requires years to traverse them. The human brain simply cannot keep these colossal scales in focus unless they are broken down into more understandable and familiar analogies. However, scale represents only one dimension of this titanic task. Even if we could somehow compress this journey into manageable timeframes, the physics of moving through space at the required speeds would generate such problems that distance itself would seem trivial. The faster we try to move, the more the universe itself seems to conspire against us, creating insurmountable obstacles. Our fastest spacecraft moves like a snail compared to interstellar distances. The Voyager 1 probe, launched in 1977, is currently traveling at 38,000 miles per hour relative to the Sun. This probe has traveled further from Earth than any other man-made object, entering interstellar space after 36 years of flight. Nevertheless, Voyager would take 73,000 years to reach Proxima Centauri, assuming it's headed in the right direction. The Parker Solar Probe currently holds the speed record, achieving 430,000 miles per hour during its closest approach to the Sun. This incredible speed is achieved by falling towards our star and using its gravity for acceleration, similar to a marble rolling down a hill. Even at this record speed, Parker would take over 6,000 years to reach Proxima Centauri. These figures reveal a fundamental problem inherent in chemical rockets. Every launch spacecraft relies on burning fuel to create the necessary thrust. However, carrying enough fuel for an interstellar journey creates an intractable equation. The more fuel you load, the heavier your spacecraft becomes, and the heavier your spacecraft, the more fuel you need to accelerate it. This vicious cycle very quickly escalates into complete absurdity. Chemical rockets reach maximum specific impulse values that make interstellar travel ridiculously impractical. Even if you built a rocket the size of a skyscraper and completely filled it with the most efficient fuel, it would only be able to accelerate a small payload to a tiny fraction of the speed required for reasonable interstellar travel. The math simply doesn't work with conventional engines, rendering such flights impossible. Consider the example of the Space Shuttle, which weighed 4.4 million pounds at launch, but delivered only 250,000 pounds to orbit. This ratio means that 94% of the total mass was fuel and engines, leaving only 6% for the payload. Scaling this approach to interstellar speeds would require fuel masses exceeding those of entire planets. Ion engines certainly offer better efficiency, but produce thrust measured in ounces, not tons. These engines can operate for years, using tiny amounts of fuel, gradually accelerating spacecraft to impressive speeds. However, even the most advanced ion engine would take centuries to achieve speeds that make interstellar travel even remotely feasible, and the spacecraft would still spend millennia reaching its destination. The speed barrier represents something far more significant than just an engineering puzzle. It unequivocally demonstrates the fundamental limitations inherent in the concept of carrying an energy source on board for a journey that spans light years. The sheer amount of energy required to send even a small spacecraft to Proxima Centauri inevitably eclipses the total energy output of all human civilization. Accelerating 1 ton of mass to 10% of the speed of light, considered a reasonable minimum for interstellar travel, requires a colossal 900 billion joules of energy. This staggering figure is equivalent to the total energy consumption of the entire United States for a period exceeding 2,000 years. These calculations, in turn, are based on an assumption of ideal efficiency. This means that 100% of the energy is directed directly to accelerating the spacecraft, allowing no losses. Real engines, by contrast, lose vast amounts of energy that dissipate as heat, light, and exhaust velocity. Chemical rockets convert less than 3% of their fuel's energy into useful thrust. Even the most advanced ion engines achieve efficiencies not exceeding 50%. Accounting for real inefficiencies multiplies energy requirements many times over, sometimes 10 or more times. The numbers become even more staggering when we consider that spacecraft must also decelerate at their destination. Newton's laws of motion operate in boundless space just as relentlessly as on Earth. An object in motion stays in motion unless acted upon by an external force. A spacecraft traveling at 10% of the speed of light would hurtle past Proxima Centauri in mere minutes if it didn't have enough fuel to slow down and enter orbit. This indispensable requirement for deceleration doubles the energy budget, assuming rocket engines are used for both acceleration and braking. Some mission designs propose using magnetic fields or radiation pressure from the destination star for deceleration, but these exotic braking systems remain purely theoretical concepts for now. Most practical proposals still require the spacecraft to carry fuel for deceleration, which doubles the already unfeasible energy requirements. Compare this to our current energy production capabilities. All power plants on Earth, nuclear, coal, gas, solar, wind, and hydroelectric, together generate about 28 trillion watts continuously. Operating every power plant on the planet for over 2 centuries would produce enough energy to send 1 ton to Proxima Centauri, assuming ideal efficiency and no other energy needs for human civilization. Building an interstellar spacecraft would require the complete dedication of all human civilization's energy output for a period exceeding all recorded history. This assumes we could store energy without loss, build perfect engines, and convince 8 billion people to live without electricity while we prepare for a journey that might ultimately fail. The energy barrier vividly demonstrates why serious proposals for interstellar missions focus on tiny payloads measured in grams, not tons. Cosmic radiation transforms the journey to Proxima Centauri into a 4-year bombardment that would cook any human crew from the inside out. Beyond Earth's protective magnetic field and atmosphere, cosmic rays streak through the solar system like invisible bullets fired from exploding stars and distant galaxies. These high-energy particles easily penetrate spacecraft hulls, equipment, and human tissues. Cosmic ray particles travel at nearly the speed of light, carrying energies millions of times greater than anything produced in Earth-bound particle accelerators. When these rays strike human cells, they shatter DNA molecules, cause cancer, and induce radiation sickness that kills within weeks. A crew making the journey to Proxima would receive radiation doses equivalent to a daily full-body CT scan for 4 consecutive years. The Sun, our star, occasionally emits powerful solar storms that make the usual background cosmic ray radiation seem insignificant. During these catastrophic events, our star ejects billions of tons of charged particles into space, moving at astonishing speeds, reaching 5 million miles per hour. Astronauts aboard the International Space Station must seek shelter in specially shielded compartments during strong solar storms. Yet even low Earth orbit provides them some protection thanks to our planet's magnetic field. A crew embarking on a journey between the stars would face these storms without any shelter other than what they could bring with them. Shielding spacecraft from radiation requires colossal amounts of material. Lead, while effective at blocking radiation, has an enormous mass, exceeding 700 pounds per cubic foot. Surrounding a crew compartment with just 3 feet of lead shielding would increase the spacecraft's mass by thousands of tons. Water, in turn, offers more economical radiation protection and serves a dual function as a source of drinking water. However, even then, effective shielding still requires layers several feet thick. The weight penalty for radiation shielding directly conflicts with the energy requirements necessary for interstellar travel. Every additional pound of shielding material multiplies the amount of fuel needed to accelerate the spacecraft. Adding sufficient shielding for a crew makes the energy requirements even more unfeasible than they already were. Mission planners face a virtually impossible choice: either expose the crew to lethal radiation or make the spacecraft so heavy it cannot reach its destination. Some designs propose using the spacecraft's fuel as radiation shielding, placing fuel tanks around the crew compartment. This approach is only effective during the early stages of the journey when the fuel tanks remain full. As the engines consume fuel during acceleration, the radiation shielding gradually disappears, exposing the crew to increasing doses of radiation as the journey progresses. Even robotic spacecraft suffer from radiation damage, which degrades electronics, solar panels, and scientific instruments throughout an interstellar journey. In the seemingly empty space between stars, there are dust particles that, upon collision at interstellar speeds, transform into veritable armor-piercing bullets. These microscopic specks of silicon, carbon, and ice drift through the galaxy at relatively low speeds, but it is the relative speed that determines the impact energy. A spacecraft traveling at 10% of the speed of light would collide with dust particles at a closing speed of 60 million miles per hour. At such speeds, even a grain of sand carries kinetic energy comparable to that of a hand grenade. The slightest dust particle, barely visible under a microscope, strikes with enough force to punch holes in steel plating. A piece of debris the size of a pebble would strike with the energy of a large bomb, potentially destroying the entire spacecraft in fractions of a second. The physics of these collisions obeys Einstein's mass-energy equation, where kinetic energy increases proportionally to the square of the velocity. Doubling the speed quadruples the impact energy in each collision. At relativistic speeds, even hydrogen atoms floating in space become dangerous projectiles that gradually erode spacecraft surfaces, much like cosmic sandblasting. Interstellar space contains approximately 1 dust particle per cubic mile, which sounds rare until you calculate the collision frequency. A spacecraft traveling to Proxima Centauri will pass through billions of cubic miles of space during its journey. The probability of colliding with dangerous debris approaches 100% over such distances and time frames. Spacecraft designers must carefully consider these collisions when planning interstellar missions. Some proposals include thick frontal shields designed to absorb dust impacts, but these shields add mass, which negatively impacts energy requirements. Other designs propose using electromagnetic fields to deflect charged particles, but this approach only works with dust particles carrying an electrical charge. The problem associated with cosmic dust impacts is significantly exacerbated as spacecraft develop increasingly higher speeds. Mission designs that envision reaching 20 or 30% of the speed of light face collision energies comparable to the power of nuclear weapons. At such colossal speeds, even the extremely diffuse hydrogen gas present in interstellar space becomes a serious obstacle, creating drag forces that gradually slow the spacecraft while simultaneously heating its outer surface to temperatures of thousands of degrees. Some theoretical concepts propose clearing a path in interstellar space using powerful laser systems capable of firing directly in front of the moving spacecraft. These beams would vaporize dust particles before the craft collides with them, thus forming a relatively clear corridor for further travel. However, the energy requirements of such laser installations prove to be comparable to the energy volumes required to accelerate the spacecraft itself. The constant threat posed by cosmic dust explains why many interstellar mission concepts predominantly focus on creating small, lightweight probes rather than developing large-scale piloted craft. Albert Einstein's theory of relativity transforms interstellar travel into a kind of journey through time itself, where the onboard clocks of rapidly moving spacecraft run significantly slower compared to clocks on Earth. At 10% of the speed of light, the effects of time dilation remain quite subtle. A 4-year journey would seem about 2 weeks shorter to the crew than to observers on Earth. However, as spacecraft approach higher fractions of the speed of light, time dilation becomes a dominant factor that radically reshapes the entire mission. A spacecraft traveling at 90% of the speed of light would experience time flowing at less than half the normal rate. The crew would age only 2 years, while 4.5 years would pass on Earth. This differential aging means that crew members return to a world that has aged much faster than they have, creating a persistent sense of alienation from the civilization they left behind. The effects of time dilation reach extreme values in the immediate vicinity of the speed of light. At 99% of the speed of light, time aboard the spacecraft slows to 1/7 of Earth's rate. A journey to Proxima, which takes 4.5 years Earth time, would be experienced by the crew as only 8 months. Travelers would return to discover, to their surprise, that everyone they knew had aged 5 times faster, transforming friends and family into elderly strangers or long-gone historical figures. These relativistic effects pose profound psychological challenges for interstellar crews. Just imagine leaving Earth with a newborn child and returning to find the child has become a middle-aged adult who barely remembers you. Spouses would age apart, friendships would vanish over time, and the crew would become temporal exiles, completely cut off from their original era. Time dilation also significantly complicates mission planning and communication systems. Ground controllers must constantly account for the fact that messages sent to a relativistic spacecraft arrive at varying speeds depending on the ship's current velocity. A conversation between Earth and the crew could take hours or even days, with time delays constantly changing as the spacecraft accelerates and decelerates. The time dilation effect also works in reverse. Crew members looking back at Earth would see events unfolding in fast forward as their spacecraft approaches the speed of light. They would observe years passing on Earth in a matter of months of ship time, witnessing changes in governments, the aging of landscapes, and the rapid march of technological progress. Some physicists propose using time dilation as an advantage rather than a drawback, designing missions where crews experience relatively short subjective travel periods, while Earth has decades to develop more advanced technologies or prepare for their return. Generation ships create psychological challenges that make physical survival seem rather straightforward. Children born aboard these giant vessels would grow up acutely aware that they would spend their entire lives traveling between the stars, never seeing a planet's surface or breathing natural air. These second and third generation crew members would inherit a mission they never chose, trapped in a metal container traversing empty space towards a destination they might never reach. The first generation of travelers would face profound trauma stemming from permanent exile from their home Earth. Crew members would watch their planet, once a haven for life, gradually shrink to a tiny point of light, realizing that the path back was forever closed to them. Every sunset, every rustle of leaves in a forest, every cool ocean breeze would transform into distant memories that would inevitably fade during the long years spent amidst recycled air and artificially generated gravity. The psychological burden of this unbreakable separation could provoke profound depression, uncontrollable anxiety, and nervous breakdowns among those who voluntarily participated in a mission from which there is no escape. Subsequent generations would face different, but no less severe, challenges. Children born within the confines of a spacecraft would experience significant difficulty understanding fundamental earthly phenomena such as weather, the changing seasons, or the boundless open sky. Their entire world would be limited to corridors, enclosed compartments, and carefully controlled ecological systems. These individuals might develop claustrophobia, agoraphobia, or other serious psychological disorders the moment they finally encounter the vast expanses of a planetary surface for the first time. Social dynamics aboard generation ships would evolve unpredictably over decades of complete isolation. Minor disagreements and petty squabbles could escalate into deep and lasting feuds, as people would be unable to escape each other's company. Religious, political, or cultural differences might splinter the crew into warring factions competing for limited resources or control of the entire mission. Children born into these divided communities would inherit conflicts whose true meaning would be incomprehensible to them, potentially leading to civil wars within the cramped confines of the spacecraft. The mission itself risks losing its original meaning over several generations. The great-grandchildren of the original crew might begin to question why they should continue towards Proxima Centauri instead of turning back or settling at some intermediate destination. Without the deep emotional connection to Earth that served as a powerful motivator for the first generation, subsequent crew members might mutiny against the mission plan or abandon the idea of interstellar travel entirely. Maintaining technological knowledge across many generations presents another significant psychological challenge. Complex spacecraft systems require experienced operators and highly skilled maintenance personnel. If key specialists die before passing on their unique skills, critically important systems could fail permanently. The psychological pressure of needing to preserve vital knowledge in complete isolation could become a source of intense stress for crew members responsible for the seamless operation of the spacecraft. Some designs propose an innovative solution, using artificial intelligence to maintain the crew's psychological health and ensure mission continuity. Maintaining human life during interstellar travel requires creating a completely closed ecosystem capable of recycling air, water, and food for generations without any external input. Every breath, every drop of water, and every calorie of food must be perfectly recycled over decades or even centuries. Even the slightest failure in these life support systems would doom the entire crew to inevitable death in the bottomless void between the stars. Air recirculation systems must efficiently remove carbon dioxide, regenerating oxygen with perfect efficiency. Plants offer one possible solution, converting carbon dioxide into oxygen through photosynthesis. However, growing enough vegetation to sustain a crew requires massive hydroponic farms. These biological systems need a constant source of light, nutrients, and careful climate control. The energy requirements for growing food in space approach those needed to propel the spacecraft itself. Water recycling becomes an even more critically important task, as water performs many vital functions aboard a spacecraft. Crew members need drinking water, but water also provides reliable radiation shielding, equipment cooling, and serves as reaction mass for engines. Advanced recycling systems can extract water from urine, sweat, humidity, and even human waste. However, these processes are extremely energy-intensive and require complex equipment that can fail during a long journey. Food production in space presents a colossal series of challenges, significantly exceeding conventional plant cultivation. To maintain a complete human diet, proteins, fats, as well as vitamins and minerals are necessary, which cannot be obtained solely from simple agricultural crops such as potatoes or wheat. Creating meat products in space remains virtually unfeasible to date, forcing spacecraft crews to rely on plant-based protein sources or synthetic substitutes. Vitamin deficiencies can provoke serious health problems during multi-year space missions. A closed ecological system must maintain a perfect balance for decades without any external inputs. Our planet's biosphere includes millions of living species that interact in extremely complex ways, ensuring nutrient cycling and maintaining a constant atmospheric composition. A spacecraft's biosphere, however, might contain only dozens of species, making it incredibly fragile and susceptible to complete collapse. The disappearance of even one key biological species could trigger a chain failure that would destroy the entire life support system. Backup systems certainly provide a certain margin of safety, but redundancy inevitably increases the mass and complicates the spacecraft's design. Chemical air scrubbers can temporarily remove carbon dioxide from the atmosphere, but they consume materials that will eventually run out. Food and water supplies can help the crew in emergency situations, but these reserves add significant mass, making interstellar acceleration more difficult. Some proposed life support systems rely on advances in synthetic biology or nanotechnology to create more efficient recycling processes. However, these advanced technologies currently remain primarily in the realm of theoretical development. Radio signals transmitted between an interstellar spacecraft and our planet Earth would experience delays that would gradually increase from minutes to years, ultimately completely cutting off the crew from the ability to communicate in real time with human civilization. Light communication seems instantaneous within Earth, but becomes agonizingly slow over interstellar distances. Messages sent from Proxima Centauri reach Earth in 4 years and 3 months, making dialogues impossible and transforming communication into a one-way exchange of historical summaries. In the initial stages of the journey, information exchange delays gradually increase as the spacecraft moves away from Earth. At a distance corresponding to that of the planet Mars, radio signals take up to 24 minutes to traverse this space, making real-time conversation impossible, but allowing for delayed message exchange. This delay continues to increase as the spacecraft moves towards the outer reaches of the solar system, reaching hours, then days. By the time the spacecraft reaches interstellar space, communication delays stretch to months or even years. A message sent from Earth would arrive when the crew had already forgotten the original question. Technical malfunctions requiring support from Earth become unsolvable, as any advice from our planet arrives significantly after the crisis has either resolved itself or led to the destruction of the spacecraft. The increasing communication delay isolates the crew both psychologically and technically. News from Earth becomes increasingly irrelevant as it arrives months or years after the events. Crew members would learn of the demise of friends and relatives long after the funerals, receive birthday greetings from people who themselves might have already passed away, and observe the development of their civilization through a series of historical snapshots rather than in real time. Radio signal power obeys the inverse square law, meaning that signal intensity decreases proportionally to the square of the distance. A radio transmission that clearly reaches from Mars becomes barely discernible noise at interstellar distances. Even the most powerful radio transmitters on Earth would struggle to send detectable signals to a spacecraft heading for Proxima Centauri. The spacecraft's own transmitters face even greater difficulties in sending signals back to Earth. Energy production aboard an interstellar spacecraft remains limited, making it difficult to operate transmitters powerful enough to reach Earth across light years of space. Solar panels become useless beyond the outer solar system, forcing crews to rely on nuclear reactors or other autonomous power sources. These communication breakdowns mean that interstellar crews must solve every problem that arises independently, completely deprived of the possibility of receiving support or assistance from Earth. Proxima Centauri appears as a fierce, highly unstable star that regularly unleashes radiation storms powerful enough to sterilize entire planets and completely destroy spacecraft. Unlike our Sun's relatively stable activity, this red dwarf erupts in massive flares, capable of increasing its brightness 10 or more times in just a few minutes. These stellar paroxysms release energy exceeding anything humanity has ever produced, spewing deadly radiation throughout the Proxima system. Red dwarfs burn their fuel so slowly that they can shine for trillions of years, outliving our Sun by thousands of times. However, this incredible longevity comes at a price. Dwarfs remain active and unstable throughout their long existence. While our Sun experiences only occasional solar storms, Proxima Centauri is in a constant state of stellar fury, regularly erupting with flares that would instantly incinerate any approaching spacecraft. These stellar flares accelerate charged particles to incredible speeds, creating radiation levels that make travel through interstellar space seem relatively safe. By comparison, a spacecraft arriving during a major flare would receive radiation doses equivalent to the detonation of nuclear weapons inside the crew compartments. Even robotic probes would suffer electronic failures that could lead to the malfunction or destruction of mission-critical systems. The planet Proxima b orbits its star at a distance of only 4 million miles, 20 times closer than Earth orbits the Sun. This tight embrace means the planet bears the full brunt of every stellar flare, lacking the protection of distance. Any atmosphere the planet might once have had was likely stripped away by billions of years of stellar bombardment, leaving behind a radiation-scorched wasteland. The star's magnetic field creates additional hazards for spacecraft attempting to approach the system. Charged particles trapped by these magnetic field lines form radiation belts similar to Earth's Van Allen belts, but thousands of times more intense. A spacecraft entering the Proxima system would have to maneuver through these deadly radiation zones while simultaneously contending with unpredictable stellar flares. Proxima b's close orbit also means the planet is likely tidally locked, with one side perpetually facing the star and the other remaining in eternal darkness. The day side would experience temperatures high enough to melt lead, while the night side would freeze to temperatures below liquid nitrogen. Any potential for life would exist only in a narrow twilight zone between these extreme environments. Even our arrival time could prove fatal. Stellar flares occur randomly, and a spacecraft could arrive during a particularly strong outburst that would instantly destroy it. Mission planners would be unable to predict stellar activity 4 years in advance, making every interstellar journey a gamble against cosmic forces beyond human control. But these destination hazards represent only the latest challenge in an already impossible journey. The propulsion technologies required to reach Proxima demand solutions that push beyond the fundamental limits of physics and engineering. Solar sails use the gentle pressure of starlight to accelerate spacecraft without using fuel. But the forces involved are so weak that sails the size of entire cities are required to achieve interstellar speeds. Light carries momentum despite having no mass, exerting tiny pressure on any surface it strikes. This radiation pressure propels solar sails much like wind propels sailboats, but the forces are millions of times weaker than even the lightest breeze. A solar sail, when directly facing the sun, experiences pressure of only 9 pounds per square mile. This weightless touch could never lift even a feather on Earth. However, in the airless vacuum of space, even such negligible forces can gradually accelerate spacecraft to impressive speeds. The main secret lies in creating sails with an enormous surface area and the lowest possible mass, ensuring a favorable thrust-to-weight ratio. For solar sails to function successfully, materials so thin they effectively become two-dimensional are required. The lightest possible sails use films just a few atoms thick, made from substances like graphene or specially designed polymers. These ultra-thin membranes reflect sunlight with virtually no mass, yet they remain incredibly fragile. The slightest speck of dust can punch holes in the sail, and solar radiation gradually degrades the material over years of exposure. The largest solar sails ever deployed were only a few hundred feet across, but interstellar missions would require sails tens of miles wide. These massive structures must unfurl perfectly in space, maintain their shape for decades of flight, and withstand impacts from cosmic dust and debris. The engineering challenges of creating and deploying city-sized sails in space surpass anything humanity has ever attempted. Solar sail acceleration rapidly decreases as it moves away from the sun. The gentle push that works effectively near Earth becomes negligible beyond Mars's orbit, limiting the use of solar sails to acceleration phases within the inner solar system. A spacecraft relying solely on solar sails would accelerate for months or even years, moving away from the sun, and then travel at a constant speed for the remainder of its interstellar journey. Advanced solar sail concepts involve using powerful lasers instead of sunlight for propulsion. These laser-driven light sails could receive concentrated energy beams from ground-based transmitters, maintaining acceleration long after leaving the solar system. However, keeping a laser focused on a distant spacecraft requires aiming precision measured in billionths of a degree, while the tiny spacecraft sail must remain perfectly aligned with the incoming beam. The combination of enormous sail sizes, ultralight construction, and precise laser aiming creates a system so complex that the slightest malfunction could lead to complete mission failure. A single tear in the sail, a momentary laser aiming error, or a software glitch in the alignment system could send the spacecraft tumbling helplessly into the bottomless void. Nevertheless, despite all these difficulties, solar sails offer one crucial advantage over all other propulsion systems. Ion engines, by contrast, maximize the efficiency of every possible kilometer of their fuel, accelerating individual atoms to incredible speeds and creating thrust so efficient that a few pounds of fuel can propel a spacecraft for years. These engines strip electrons from xenon atoms or other gases, forming charged particles known as ions. Powerful electric fields then accelerate these ions to speeds reaching 60,000 miles per hour before ejecting them from the rear of the engine as exhaust. The exhaust velocity of ion engines exceeds that of chemical rockets by 10 or more times, which directly translates into fuel efficiency via the rocket equation that governs all spacecraft. While chemical rockets expel hot gases at speeds of a few thousand miles per hour, ion engines achieve exhaust velocities approaching 200,000 miles per hour. This incredible efficiency means that ion engines can accelerate spacecraft to significantly higher final speeds while using considerably less fuel. The trade-off is thrust levels that are barely registered by conventional dynamometers. Ion engines produce thrust measured in ounces, not tons, creating acceleration so gentle that crew members would not feel it at all. A spacecraft using ion engines could slowly climb out of Earth's gravitational well over many months, gradually gaining speed due to the weak but continuous thrust. This gentle acceleration is an undeniable advantage for interstellar missions, where travel times can be years or even decades. Ion engines have the ability to operate continuously throughout the journey, accelerating the ship during the first half of the trip and then reversing to decelerate during the second half. Constant thrust allows for a steady buildup of speeds that chemical rockets could never achieve, even with unlimited fuel supplies. Modern ion engines consume electrical power measured in kilowatts, requiring extensive solar arrays or powerful nuclear reactors for their operation. For example, the Deep Space One mission used solar panels the size of a basketball court to power a single ion engine that produced only 2 ounces of thrust. Scaling this approach to interstellar speeds would require power systems comparable in output to entire cities. Advanced ion engine concepts propose using nuclear reactors or even fusion power plants to generate the colossal electrical power needed for high-thrust operation. These nuclear electric propulsion systems could create thousands of times more thrust than modern ion engines while maintaining their exceptional fuel efficiency. However, developing nuclear reactors capable of reliably functioning for decades in the harsh radiation environment of space remains an unsolved engineering challenge. The mathematical elegance of ion engines lies in their ability to approach the theoretical limits of rocket efficiency. Unlike chemical rockets, which waste a significant portion of their energy heating exhaust gases, ion engines convert electrical energy directly into kinetic energy with minimal losses. This high efficiency means that ion-propelled spacecraft could eventually reach 10 or 20% of the speed of light with sufficient time and electrical power. But even the most advanced ion engines face fundamental limitations that prevent them from reaching truly relativistic speeds. Nuclear pulse propulsion utilizes the explosive power of atomic bombs to accelerate spacecraft, detonating nuclear charges behind massive shock absorbers that convert the blast energy into forward motion. This concept might seem like pure science fiction until one realizes that nuclear explosions represent the most concentrated energy sources available to human technology, capable of accelerating large spacecraft to speeds far exceeding anything achievable with chemical rockets. Project Orion, seriously studied by NASA and the U.S. Air Force in the 1960s, proposed dropping nuclear bombs from the rear of a spacecraft and riding the explosions like a cosmic pogo stick. Each blast would strike a massive steel pusher plate connected to the crew compartment via powerful shock absorbers. Repeated nuclear explosions would gradually accelerate the spacecraft to incredible speeds, while the shock absorption system protected the crew from being crushed by the acceleration forces. The numbers behind nuclear pulse propulsion demonstrate its incredible potential. A single nuclear weapon releases energy equivalent to thousands of tons of chemical explosives, enough to accelerate a massive spacecraft by hundreds of miles per hour with each blast. A chain of hundreds or thousands of nuclear explosions could theoretically accelerate a spacecraft to significant fractions of the speed of light, making interstellar travel possible within a human lifetime. Nuclear pulse propulsion systems could carry enormous payloads compared to other propulsion concepts. Where ion engines and solar sails work only with light probes, nuclear pulse ships could transport entire crews, life support systems, and scientific equipment to other star systems. Massive pusher plates and shock absorbers certainly add weight to the spacecraft, but nuclear explosions provide enough energy to accelerate these heavy systems along with substantial payloads. The engineering challenges associated with nuclear pulse propulsion seem almost incredible, bordering on insanity. The pusher plate, a key structural element, must withstand numerous nuclear detonations without melting, cracking, or detaching from the spacecraft. The shock absorption system is designed to mitigate colossal acceleration forces that would otherwise crush the crew, while the nuclear charges themselves must detonate at a strictly defined distance and at precisely timed intervals to maximize thrust efficiency. The radiation emanating from nuclear explosions would inevitably cook both the crew and equipment, if not for massive shielding protecting the spacecraft. Each nuclear detonation generates an electromagnetic pulse capable of destroying electronic systems, and neutron radiation would gradually render the entire spacecraft radioactive. The crew, in essence, would be inside a nuclear reactor that periodically explodes behind them. Environmental and political considerations make nuclear pulse propulsion virtually impossible to test or deploy. Detonating nuclear weapons in space violates numerous international treaties. Furthermore, radioactive fallout from launches would contaminate vast areas around the launch site, and public opposition to nuclear-powered spacecraft has hindered the advancement of even the most modest nuclear propulsion programs. Nevertheless, nuclear pulse propulsion remains one of the few technologies that could realistically send large crewed spacecraft to nearby stars within a reasonable time frame. Antimatter represents the ideal rocket fuel, capable of converting 100% of its mass directly into energy through annihilation reactions that make nuclear explosions seem like firecrackers. When matter and antimatter meet, they completely destroy each other, releasing energy. According to Einstein's famous equation, 1 pound of antimatter reacting with 1 pound of ordinary matter would release energy equivalent to 43 million tons of conventional explosives. This perfect energy conversion makes antimatter the holy grail of space propulsion. Chemical rockets lose most of their energy heating exhaust gases, while nuclear rockets convert less than 1% of their fuel's mass into energy. Antimatter engines could theoretically achieve exhaust velocities approaching the speed of light itself, allowing spacecraft to reach relativistic speeds that make interstellar travel practically feasible within a single human lifetime. The mathematics of antimatter propulsion approaches theoretical perfection. Just a few ounces of antimatter could accelerate a large spacecraft to 10% of the speed of light, reducing the travel time to Proxima Centauri from tens of thousands of years to a few decades. Fuel requirements are reduced to manageable levels, eliminating the unfeasible energy budgets that plague other propulsion concepts. Creating antimatter requires the most advanced particle accelerators on Earth, which consume enormous amounts of electricity to produce microscopic quantities of antiprotons and positrons. Current production rates measure antimatter in individual atoms, not in usable quantities. Producing 1 gram of antimatter would require all the electricity of the United States for thousands of years using current technology. Storing antimatter presents challenges that make handling nuclear fuel seem simple. Antimatter cannot touch ordinary matter without instantaneous annihilation, requiring containment systems that use magnetic fields to suspend antimatter particles in a perfect vacuum. These magnetic traps must operate flawlessly for years or decades, as any containment failure would release the entire fuel supply in a matter-antimatter explosion that could vaporize the spacecraft. The annihilation reactions, so perfectly suited for using antimatter as fuel, simultaneously generate deadly radiation capable of incinerating any nearby crew. Antimatter engines would require massive radiation shielding to protect humans. While intense energy releases can damage or completely destroy engine components during operation, the engineering challenges involved in designing engines capable of withstanding repeated matter-antimatter explosions currently remain primarily in the realm of theoretical discussions. Even infinitesimally small quantities of antimatter become incredibly dangerous if they fall into the wrong hands. Just a few grams of antimatter could form the basis for a weapon possessing destructive power exceeding the largest nuclear bombs ever created. The security requirements for producing, storing, and transporting antimatter would rival the complexity of nuclear weapons programs, adding political and military difficulties to any space mission using antimatter. Despite all these complexities, antimatter remains the only known technology that could potentially enable rapid interstellar travel using realistic fuel volumes. Ramjet fusion engines have been proposed as a solution to the fuel problem, implying eating their way through space. They gather hydrogen atoms from the interstellar medium and burn them in nuclear fusion reactions, propelling the spacecraft forward. This concept eliminates the need to carry fuel for the entire journey, as the craft instead collects it from space itself as it moves between stars. The interstellar medium contains approximately 1 hydrogen atom per cubic centimeter, which is an extremely low concentration by Earth standards. However, this amount could potentially be collected by a spacecraft equipped with massive magnetic field generators. These electromagnetic scoops would extend thousands of miles ahead of the spacecraft, gathering hydrogen atoms and funneling them into fusion reactors that burn the hydrogen, converting it into helium and releasing colossal amounts of energy in the process. The Bussard ramjet, named after physicist Robert Bussard, who proposed the concept, would continuously accelerate throughout its journey, consuming interstellar hydrogen. The faster the spacecraft moves, the more hydrogen it encounters per unit of time, which increases the fuel flow rate and potentially allows the ramjet to accelerate to significant fractions of the speed of light. This self-sustaining propulsion system could theoretically reach speeds that make interstellar travel practically feasible. The magnetic field generators required to collect hydrogen are significantly beyond any currently available technology. The electromagnetic scoop would have to extend thousands of miles into space, generating magnetic fields strong enough to deflect and capture individual hydrogen atoms moving at relative speeds of millions of miles per hour. The energy requirements for these magnetic fields are comparable to those needed to accelerate the spacecraft itself. Nuclear fusion reactions require temperatures of hundreds of millions of degrees and pressures found exclusively in stellar cores. Creating controlled fusion reactions on Earth remains an unsolved engineering challenge, despite decades of research and billions of dollars spent on development. Building fusion reactors that reliably operate in space while processing hydrogen collected from the interstellar medium represents an even greater technological leap. The ramjet concept faces a fundamental catch-22 problem that might render it impossible to implement. The spacecraft must move at relativistic speeds to collect enough hydrogen to sustain fusion reactions. But achieving these speeds in the first place requires conventional propulsion systems, which face all the fuel and energy limitations discussed earlier. The ramjet cannot begin to operate until the spacecraft is already approaching speeds that cannot be achieved by other propulsion systems. Detailed physical calculations demonstrate that ramjet engines, contrary to the initial idea, may not accelerate, but rather decelerate at high speeds. The drag forces arising from moving through the interstellar medium at relativistic speeds can significantly exceed the thrust generated by burning the collected hydrogen. Such a phenomenon would transform the ramjet from a propulsive force into an effective brake, gradually slowing the spacecraft until it comes to a complete halt in the vast expanses of interstellar space. Nevertheless, this fascinating ramjet concept continues to serve as a source of inspiration for developing new variations designed to overcome these seemingly fundamental, insurmountable limitations. Project Breakthrough Starshot proposes a revolutionary approach involving the creation of a laser system powerful enough to accelerate miniature spacecraft to 20% of the speed of light. This would use concentrated light beams to propel ultralight probes towards Proxima Centauri in just 20 years. This ambitious project completely excludes human crews, focusing on the use of miniature robots whose size allows them to sail on laser light waves across vast interstellar distances. Implementing this concept requires building a complex of ground-based lasers with a total power output reaching gigawatts, equivalent to the power of several nuclear power plants operating simultaneously. These laser installations would focus their energy into narrow beams capable of imparting motion to small spacecraft equipped with ultralight solar sails. The intense laser light would accelerate the probes to incredible speeds within minutes, sending them on trajectories that would allow them to reach Proxima Centauri faster than any other mission ever proposed. Each Starshot probe would weigh less than 1 gram, roughly comparable to the mass of a computer chip equipped with cameras, sensors, and communication equipment. These gram-scale spacecraft represent the highest degree of miniaturization in space technology, housing scientific instruments in bodies smaller than postage stamps. Advanced manufacturing technologies, borrowed from the field of computer chip fabrication, would theoretically allow thousands of such tiny probes to be built at the cost of one conventional spacecraft. The laser acceleration phase would last only a few minutes, during which the probes would experience acceleration forces millions of times greater than Earth's gravity. These extreme loads would simply crush any standard spacecraft. However, gram-scale probes can survive due to their minimal size and low mass, which promotes a more even distribution of acceleration forces. The probes would need to maintain impeccable orientation during acceleration, keeping their solar sails perfectly aligned with the laser beam, despite the colossal forces capable of tearing apart larger spacecraft. Keeping a laser beam focused on a tiny spacecraft moving at 20% of the speed of light requires aiming precision exceeding anything ever achieved. The laser system would need to track targets smaller than computer chips over distances of trillions of miles, compensating for atmospheric distortions, Earth's rotation, and the spacecraft's own motion. An aiming error less than the width of a human hair could result in the laser completely missing its target. The probes would not be able to slow down when they reach Proxima Centauri, as they would have no fuel for braking. Instead, they would hurtle past the Proxima system at 20% of the speed of light, collecting data during a flyby lasting only a few hours. Scientific observations would have to occur entirely automatically, as radio signals would take over 4 years to travel the distance between Earth and Proxima. Communication with the probes presents its own, equally significant challenges. Gram-scale spacecraft cannot carry powerful radio transmitters, forcing them to rely on weak signals that become barely discernible at interstellar distances. Ground-based radio telescopes would need to search for signals thousands of times weaker than current detection limits, assuming the probe's transmitter survives a 20-year journey through space. Despite these significant difficulties, Project Breakthrough Starshot still represents the most practically feasible and realistic approach to interstellar exploration in the short term. The concept of suspended animation could transform the psychological nightmare of multi-year interstellar journeys into a serene and peaceful sleep, allowing crews to skip decades of wandering and awaken fully rested directly at their destination. This unique idea is borrowed from the natural process of hibernation observed in various animals, such as bears, ground squirrels, and many others, capable of slowing their metabolism during cold winter months. Extending these profound biological processes to human timescales could make journeys lasting centuries psychologically manageable and acceptable. Medical researchers have already achieved some, albeit limited, success with therapeutic hypothermia, cooling patients during complex surgical operations to slow their metabolism and significantly reduce tissue damage. These medical procedures typically last only a few hours, not years, but they convincingly demonstrate that human metabolism can be safely slowed under strictly controlled conditions. However, scaling therapeutic hypothermia to decades or even centuries would require solving colossal medical and technical challenges. Deep hibernation significantly slows animal metabolism by 10 or more times, allowing these creatures to survive for many months without food while consuming minimal oxygen. Their heart rate drops to a few beats per minute, brain activity becomes barely discernible, and body temperature drops to near freezing. These hibernating animals essentially suspend their lives, emerging in spring with minimal aging despite months of complete inactivity. Research into human hibernation remains in its earliest stages, but scientists have already identified some key biological mechanisms that control the hibernation process in animals. Specialized hormones trigger the hibernation response, while other biochemical changes effectively protect cells from damage during prolonged periods of reduced metabolism. A deep understanding and subsequent replication of these complex processes in humans could eventually enable artificial hibernation for future space travel. Suspended animation systems would have to reliably maintain crew members in a hibernative state for many decades, while meticulously monitoring their health and preventing any possible medical emergencies. Automated medical systems would have to provide nutrition, effectively remove waste products, and promptly treat any health problems that might develop during prolonged sleep. These extremely complex life support systems must function flawlessly throughout the interstellar journey. Since crew members would not be able to wake up to fix malfunctions, the hibernation process itself carries significant medical risks, potentially leading to the death of crew members before they reach their final destination. Cooling the human body causes numerous physiological changes that can provoke heart problems, blood clot formation, organ failure, and irreversible brain damage. Current therapeutic hypothermia procedures require constant medical supervision, making them completely impractical for multi-year applications without significant technological breakthroughs. Awakening from decades of suspended animation could prove as dangerous as the sleep process itself. The human body would require careful rewarming and prolonged rehabilitation to fully restore normal functions after many years of inactivity. Muscle atrophy, significant bone loss, and neurological changes could leave crew members weak or even incapacitated precisely when they need to be at peak performance for exploring new planets. Some hibernation concepts propose partial rather than complete metabolic shutdown, maintaining crew members in a twilight state between sleep and consciousness. Artificial intelligence could completely eliminate the need for human crews, sending robotic explorers who never experience loneliness, never need food or air, and never worry about returning home. These mechanical envoys could withstand radiation doses that would instantly kill humans, operate in a vacuum without life support systems, and remain functional for centuries while traveling between stars. Advanced artificial intelligence could even make more effective decisions than human crews when facing unexpected and complex challenges of interstellar exploration. Modern spacecraft already rely heavily on autonomous systems that navigate, communicate, and conduct scientific observations without direct human involvement. For example, Mars rovers can function independently for many months, making their own decisions about routes and selecting scientific targets using advanced artificial intelligence systems. Scaling these capabilities to interstellar missions would require the development and implementation of artificial intelligence systems capable of fully independent operation for decades, as any possibility of human assistance in such conditions would be absent. Robotic spacecraft have the unique advantage of being able to survive in the harsh radiation environment of interstellar space without the need for massive shielding that is absolutely essential for human crews. Electronic components can be significantly hardened against radiation damage through the application of special materials and innovative design methods, which would be completely impractical for biological systems. Although cosmic rays will inevitably gradually degrade electronic components over time, the use of redundant systems will compensate for possible failures throughout the multi-decade journey. The mass savings achieved by completely eliminating life support systems would significantly enhance the feasibility of interstellar missions. Human crews need air, water, food, as well as extensive radiation shielding and living space, which adds thousands of tons to the spacecraft's total mass. Robotic explorers, by contrast, only require their scientific instruments, communication equipment, and propulsion systems. Such a significant reduction in mass directly contributes to achieving higher speeds or reducing the energy requirements needed to reach interstellar velocities. Artificial intelligence systems could potentially make more effective scientific decisions than human crews, especially during a brief flyby of an alien star system. AI systems can process information significantly faster than humans, analyze multiple options simultaneously, and optimize scientific observations in real time. In situations where every second is crucial during a high-speed encounter with an unknown world, artificial intelligence could maximize the scientific return of the mission. The development of general artificial intelligence capable of fully autonomous interstellar exploration remains decades away, despite rapid advances in machine learning and robotics. Modern AI systems excel at performing specific tasks, but they lack the flexibility and creativity necessary for open-ended exploration of unknown environments. Creating AI systems capable of functioning independently for decades, adapting to unforeseen challenges, represents one of the greatest technical hurdles in computer science. Communication delays mean that robotic explorers will have to make critical decisions without any input or instructions from Earth. A robot facing unexpected obstacles or opportunities in the vicinity of Proxima Centauri will not be able to wait 4 years for instructions from ground controllers. Artificial intelligence will have to assess situations, weigh various options, and choose optimal courses of action with the same degree of independence as human explorers. Programming ethical decisions into artificial intelligence systems becomes a crucial factor when robots operate without direct human oversight. Generation ships must be large enough to contain entire civilizations, creating self-sufficient worlds that will carry thousands of people through the void between stars. These massive vessels would dwarf anything humanity has ever built, stretching for miles and containing forests, lakes, and agricultural lands large enough to sustain diverse ecosystems. The engineering challenges of building city-sized spacecraft push beyond the fundamental limits of material science and structural engineering. The smallest viable generation ship would need to accommodate at least 10,000 people to maintain genetic diversity and preserve human culture over a centuries-long journey. This population requires living space equivalent to a large city, along with all the infrastructure needed for manufacturing, agriculture, education, and governance. The spacecraft would essentially become a floating nation traversing interstellar space without any possibility of external assistance. Artificial gravity becomes a vital necessity for ensuring human well-being during multi-generational space expeditions, as prolonged exposure to weightlessness inevitably provokes bone degradation, muscle fiber atrophy, and the development of serious cardiovascular diseases, which undoubtedly poses a direct threat to the health and lives of the crew. The most feasible and practically implementable approach to creating artificial gravity is to rotate the entire spacecraft, which generates centrifugal force mimicking gravitational effects. However, to achieve Earth-level gravity, colossal rotating structures must be built, whose diameter must be measured not in feet but in miles. At the same time, the structural loads arising in such interstellar generation ships reach critical values, approaching the strength limits of all currently known materials. The outer sections of the spacecraft would be subjected to forces equivalent to dozens of Earth gravities, necessitating the use of construction materials surpassing steel in strength to prevent catastrophic structural failure. Modern high-tech materials such as carbon nanotubes could provide the required strength, but methods for manufacturing large-scale, mile-long structures from these materials currently remain exclusively in the realm of theoretical research. The closed ecological systems housed aboard generation ships would have to function flawlessly for many centuries without any external resource inputs. The ship's biosphere would have to completely recycle all organic matter, maintain a stable atmospheric gas composition, and support diverse forms of plant and animal life without having the backup systems that exist on Earth. Even a single ecological catastrophe could doom the entire population to starvation or suffocation in the airless void of space. Social and political systems aboard generation ships would evolve in complete isolation from Earth, potentially leading to the formation of entirely new forms of human civilization by the time the ship arrives at its destination. The children and grandchildren of the original crew might develop unique languages, customs, and political structures fully adapted to the specifics of life aboard a spacecraft. These cultural transformations could make communication with Earth increasingly complex and difficult as the interstellar journey progresses. The economic cost of building generation ships would significantly exceed the gross domestic product of entire nations. Constructing spacecraft measured in miles requires millions of tons of materials, manufacturing capabilities that significantly surpass current industrial capacities, and a workforce comparable in scale to the largest infrastructure projects on Earth. The financial investment required to implement a generation ship project could demand unprecedented cooperation among several nations, or radical changes in how human civilization allocates resources. Nevertheless, generation ships offer one undeniable and decisive advantage over all other approaches to interstellar colonization. Interstellar travel is so expensive that only the threat of complete human extinction could justify the colossal economic investment required to send humans to other star systems. The cost of building generation ships or developing advanced propulsion systems exceeds the gross domestic product of entire nations, demanding a level of international cooperation and resource allocation that humanity has never before achieved. Only a final insurance policy against cosmic catastrophe could serve as sufficient motivation for such enormous expenditures. Consider the economic scale of building a generation ship capable of carrying 10,000 people to Proxima Centauri. The materials alone would require mining operations that would dwarf all currently existing ones. Furthermore, the manufacturing infrastructure needed to build spacecraft measured in miles does not exist anywhere on Earth. Conservative cost estimates reach hundreds of billions or even trillions of dollars, representing a significant fraction of global economic output. These costs only become manageable when compared to the value of humanity's survival itself. Earth faces numerous existential threats that could end human civilization within centuries or millennia. Asteroid impacts, supervolcanic eruptions, gamma-ray bursts, and risks associated with artificial intelligence development all represent potential extinction scenarios that would make interstellar travel investments seem trivial in comparison. Spending trillions of dollars to create backup colonies begins to seem quite reasonable when the alternative is complete and irreversible extinction. The economic rationale for interstellar colonization is based on the same fundamental logic as applying insurance policies in everyday life. Individuals make certain payments monthly, seeking to protect themselves from unlikely but potentially catastrophic incidents, such as sudden house fires or serious car accidents. Similarly, sovereign states make significant investments in developing military defense systems designed to prevent attacks that may never occur. In this context, interstellar colonies represent the ultimate form of insurance policy, designed to protect human civilization from existential risks capable of simultaneously destroying every inhabitant of Earth. Financial models developed for interstellar missions must account for economic returns that span time horizons of hundreds or even thousands of years, which is radically different from typical short-term business frameworks. The resources and invaluable knowledge accumulated in the process of creating interstellar colonies could ultimately offset the initial capital expenditures. However, these future returns would benefit future generations, not those who made the initial investments. Traditional economic analysis proves inapplicable when considering projects characterized by centuries-long timescales and aimed at mitigating existential threats. International cooperation becomes absolutely essential for implementing any realistic interstellar colonization program. Since no single nation possesses sufficient resources required to build generation ships or develop advanced propulsion systems, the political challenges associated with maintaining international cooperation over multi-century projects rival the complexity of the interstellar journey itself. Economic interests, political disagreements, and frequent changes in leadership can derail interstellar programs long before spacecraft reach their final destinations. Private funding could eventually contribute to interstellar research as wealthy individuals and large corporations recognize the long-term value of species survival. Technological entrepreneurs who have built trillion-dollar companies could view interstellar colonization as the ultimate grand project worth pursuing, regardless of immediate economic returns. Nevertheless, exclusively private funding is insufficient to cover the colossal costs of building generation ships or developing fundamentally new engines. The economics of species survival ultimately depends on how highly human civilization values its own continued existence. Proxima b is a world of extremes, where one hemisphere blazes under eternal daylight, while the other freezes in perpetual night, creating conditions unlike anything in our solar system. This alien Earth orbits so close to its red dwarf star that powerful gravitational forces have locked it in place, forcing the same side to always face Proxima Centauri. The result is a planet divided between fire and ice, with potentially habitable conditions existing exclusively in a narrow twilight zone located between these two extremes. Proxima b's day side is exposed to temperatures high enough to melt lead, with surface conditions that would vaporize any spacecraft unlucky enough to land there. Stellar radiation from the nearby red dwarf bathes this hemisphere in energy levels exceeding those found on Venus, creating an infernal landscape of superheated rock and possibly flowing molten lava. Any atmosphere on the day side would be stripped away by the intense stellar wind and radiation pressure. The night side presents equally hostile conditions, but for diametrically opposite reasons. Constant darkness and complete isolation from stellar heat would lead to temperatures approaching absolute zero, cold enough to freeze carbon dioxide and nitrogen into solid ice. This frozen wasteland would be as lifeless as Pluto's surface, with no energy sources to sustain any form of biological activity. Spacecraft landing on the night side would face challenges similar to those encountered when operating in the outer solar system. Between these polar extremes, where either scorching heat or freezing cold reigns, lies the twilight zone. It is here, in this thin strip girdling the planet, that conditions theoretically could allow for the existence of liquid water on the surface. This narrow band around the celestial body represents the only potentially habitable region where a delicate balance between stellar heating and radiative cooling can create Earth-like conditions. However, as scientists predict, this twilight zone would be constantly subjected to hurricane-force winds as superheated air from the day side rapidly moves towards the cold night side. Proxima b's atmospheric dynamics would likely create weather phenomena completely unlike those observed on Earth. The significant temperature difference between the day and night sides would drive powerful atmospheric circulation, with wind speeds potentially reaching hundreds of miles per hour. These relentless storms would make landing any spacecraft an extremely dangerous undertaking. While furious winds would rapidly erode any surface formations through constant sandblasting, stellar flares emanating from Proxima Centauri would periodically sterilize any life forms that might exist on the planet's surface. Such radiation bursts occur entirely randomly and without any prior warning, delivering doses of high-energy particles capable of instantly killing unprotected organisms. Consequently, any potential life on Proxima b would have to seek refuge underground or in deep waters to survive these periodic sterilization events threatening its existence. This planet's magnetic field, if it exists at all, would be significantly weaker than Earth's powerful protective magnetosphere. Without adequate magnetic protection, the stellar wind from Proxima Centauri would gradually strip away any atmosphere the planet might possess. This atmospheric erosion likely occurred over billions of years, potentially leaving behind only a thin residual atmosphere or even none at all. Despite all these serious difficulties, Proxima b still remains our best target for interstellar exploration. This is due to the simple fact that it represents the closest potentially rocky planet to Earth located outside our solar system. Radio waves travel at the speed of light, making them the fastest messengers we could send to announce our arrival at Proxima Centauri years before any spacecraft reaches that star system. These electromagnetic signals could carry detailed information about human civilization, our scientific knowledge, and peaceful intentions to any intelligent life that might exist around our nearest stellar neighbor. A carefully crafted radio message could become humanity's first diplomatic contact with an extraterrestrial civilization. Powerful radio transmitters located on Earth are capable of sending signals strong enough to be detected over interstellar distances. Assuming alien civilizations possess radio telescopes similar to ours, the Arecibo radio telescope, before its collapse, could have detected signals from an identical telescope located within 1,000 light years. This assumption allows us to believe that advanced civilizations around Proxima Centauri could receive and decode radio messages transmitted from Earth using modern technology. The content of such a message would require extremely careful consideration to ensure its understanding by a non-human intelligence. Mathematical concepts, such as prime numbers or geometric relationships, could serve as universal languages that any scientific civilization would undoubtedly recognize. Drake's famous equation, which estimates the probability of extraterrestrial intelligence, itself could be transmitted as a way of demonstrating human scientific understanding and our awareness that other civilizations might exist. Encoding human knowledge into radio signals presents fascinating challenges that reveal hidden assumptions underlying our own communication methods. How do you explain color to beings who might perceive entirely different wavelengths of light? How do you describe music to beings who may not have auditory systems like ours? The process of creating interstellar messages involuntarily forces us to deeply reflect on which aspects of the human experience might be universal and which are culturally specific. Signal transmission time is a key factor when planning the coordinated arrival of radio messages and spacecraft. Radio waves sent from Earth today will reach the Proxima Centauri system in 4 years and 3 months. In contrast, spacecraft using existing propulsion technologies would take 10,000 years or even more to complete the same journey. However, if humanity develops advanced propulsion systems, this would reduce spacecraft travel time to a few decades, potentially allowing radio messages and physical visitors to arrive in the same historical period. From the perspective of extraterrestrial civilizations, multiple signal transmissions can serve as a reliable redundancy system, guarding against possible technical failures or atmospheric interference that might occur around Proxima Centauri. Repeatedly sending an identical message using different radio frequencies and transmission methods would significantly increase the probability that at least some signals reach their final destination intact. Beyond practical utility, such redundant transmissions can also vividly demonstrate human persistence and unwavering commitment to establishing interstellar communication. The power requirements for interstellar radio communication remain quite manageable compared to the colossal amount of energy needed for spacecraft propulsion. The largest radio transmitters on Earth consume electrical power measured in megawatts, while advanced spacecraft engines would require gigawatts of energy. This circumstance makes radio communication an accessible and logical first step towards interstellar contact, which can be taken long before humanity develops practical and efficient interstellar propulsion systems. However, it should be remembered that sending radio signals reveals our location and technological capabilities to any civilizations that may have hostile intentions. Interstellar missions carry such enormous risks that responsible mission planning invariably requires multiple backup spacecraft, redundant systems, and alternate destinations. This is necessary to guarantee the success of at least part of humanity's interstellar endeavors. The vast distances and multi-decade travel times mean that even single failures can doom entire missions, nullifying centuries of preparation and astronomical investments. Only through meticulous redundancy planning can interstellar missions achieve acceptable probabilities of success. Launching multiple spacecraft to the same destination would provide robust insurance against individual mission failures that can occur due to technical malfunctions, navigation errors, or collisions with space debris. If, for example, 5th-generation ships were to depart for Proxima Centauri using different launch windows and trajectory profiles, the probability of at least one mission succeeding drastically increases compared to staking everything on a single spacecraft. This redundancy comes with enormous financial costs, but remains absolutely necessary for missions that cannot be repeated or rescued. Backup destinations become critically important when primary targets prove unsuitable for colonization or hostile to human life. Recent exoplanet discoveries have revealed potentially habitable worlds around nearby stars such as Tau Ceti, Wolf 359, and Gliese 687cc. Developing interstellar missions to multiple destinations simultaneously would hedge against the possibility that Proxima b is uninhabitable, or that one particular mission encounters insurmountable obstacles. Different propulsion technologies must be developed simultaneously to avoid reliance on any single approach that might prove technically impossible or economically unfeasible. While some missions might utilize nuclear pulse propulsion, others could employ ion engines, solar sails, or advanced fusion systems. This technological diversification ensures the continuation of interstellar research, even if specific propulsion concepts do not meet their performance targets. Robotic precursor missions could play a key role, exploring potential destinations decades in advance of human crews. These Vanguard probes would provide invaluable information about specific local conditions and help identify the most promising locations for future colonies. Small robotic probe craft, equipped with laser propulsion, could reach our nearest star systems in approximately 20 to 30 years, gathering crucial data on planetary environments, radiation levels, and potential resource sources. Such advanced reconnaissance would allow subsequent human missions to focus optimally on the most suitable and safe destinations. Communication relay networks, strategically located between Earth and distant interstellar destinations, would be able to maintain continuous contact with remote spacecraft throughout their multi-year journey. These relay stations, envisioned to be equipped with nuclear reactors for power and powerful radio transmitters, would significantly extend the range of communication systems and provide reliable backup data channels in case of primary system failure. Furthermore, such a relay network would enable effective coordination between multiple concurrent missions and facilitate the prompt exchange of critical information between different spacecraft. Automated manufacturing systems integrated aboard interstellar spacecraft would have the ability to fabricate spare parts and replacement equipment directly during the long journey. This would significantly reduce reliance on components that could potentially fail after decades of operation in space. Three-dimensional printing technologies, combined with robotic assembly systems, could produce virtually everything, from miniature electronic components to large structural materials, using raw materials transported aboard the spacecraft or extracted from asteroids encountered along the way. The ultimate and most reliable backup plan involves establishing self-sustaining human populations in not one, but several star systems simultaneously. This approach reduces risks and avoids reliance on single colonies that might fail due to local catastrophes or unfavorable environmental changes. At first glance, the seemingly impossible journey to Proxima Centauri represents humanity's only long-term strategy for survival in the face of cosmic threats that could potentially end our species within the next few centuries or millennia. Our Earth exists in a dangerous universe, abundant with asteroid impacts, supervolcanic eruptions, gamma-ray bursts, and other catastrophic events that have repeatedly caused mass extinctions throughout the planet's geological history. Establishing self-sustaining colonies around other stars would ensure the survival of human civilization, even if Earth becomes uninhabitable for any reason. Dinosaurs dominated Earth for over 160 million years before an asteroid impact ended their reign in mere hours. Similar cosmic catastrophes await our planet on timescales that may seem distant to individuals, but represent only moments in the grand history of the universe. Without interstellar colonies, humanity remains vulnerable to single events that could simultaneously annihilate every human on Earth, thereby ending 4 billion years of biological evolution in our corner of the galaxy. The development of interstellar travel technologies would transform human civilization in ways that extend far beyond mere species survival. The engineering challenges involved in building generation ships, developing fusion rockets, and creating life support systems for centuries-long journeys would undoubtedly stimulate technological advancements that would truly revolutionize life on Earth. Energy production, material science, artificial intelligence, and closed ecology, all these areas would rapidly evolve to meet the extremely high demands of interstellar exploration. The shift in perspective that would occur from becoming an interstellar species could fundamentally change how humans view themselves and their place in the universe. Political conflicts over national borders would seem utterly trivial when viewed on the scale of light years. Meanwhile, environmental problems that now seem insurmountable could be successfully solved using technologies developed for spacecraft life support systems. Interstellar exploration would inevitably force humanity to think and plan on timescales measured in centuries rather than short election cycles. Breakthroughs in science achieved through interstellar endeavors could provide comprehensive answers to profound questions about the essence of being, the nature of mind and consciousness that permeate the entire universe. The discovery of organic life beyond our planetary system would convincingly demonstrate that biological processes are a ubiquitous phenomenon, not merely a cosmic coincidence unique to Earth. The detection of extraterrestrial civilizations would undoubtedly cause a radical upheaval in our understanding of thought, technological progress, and the potential paths of development open to intelligent beings. The long-term economic returns from colonizing other star systems would undoubtedly repay the colossal initial investments. Human communities settled around distant stars would inevitably drive innovation, mastering new technologies, benefiting from extraterrestrial resources, and building vast trade routes stretching for many light years. Such interstellar economies would serve as reliable repositories of knowledge, cultural heritage, and genetic diversity, allowing Earth not only to recover from future cataclysms, but also to ensure the continuous progressive development of all human civilization. Ultimately, the expedition to Proxima Centauri signifies much more than merely moving to another stellar body. It embodies a fundamental shift in humanity's destiny, from a vulnerable planet-bound species susceptible to cosmic cataclysms to the status of an interstellar civilization possessing the potential to spread life and intelligence across the boundless expanses of the galaxy. The technical barriers appear colossal, the financial costs astonishing, and the required time horizons stretch far beyond a single human lifetime. However, the alternative to this grandiose endeavor seems to be inevitable decline. Humanity has already blazed its trail through the crushing infinity of space, confronted radiation storms capable of incinerating all life, and faced energy demands whose scale exceeds the capabilities of all Earth civilization. Every new mile closer to Proxima Centauri reveals previously unknown obstacles that seem designed to forever trap us on this small blue world. Yet, it is precisely in these seemingly insurmountable difficulties that the greatest opportunity lies for the human race to overcome its planetary limitations and transform into something significantly grander than its current state. The same species that once huddled around campfires, trembling at the impenetrable darkness beyond, has now sent its robotic messengers to every planet in the solar system. Representatives of humanity have split the atom, deciphered their own genetic code, and created thinking machines. This proves that the impossible has a curious ability to become the inevitable when humans are firmly determined to achieve it. The expedition to Proxima Centauri will require overcoming challenges that currently seem beyond the reach of modern human engineering and imagination. However, perhaps it is precisely such a challenge that is needed, a challenge so grand that it will inspire humanity to evolve, to cooperate closely, and to transcend the fleeting conflicts that divide our species today. The technological innovations developed for interstellar travel will fundamentally transform life on Earth. At the same time, the very idea of becoming an interstellar civilization will deeply change humanity's self-perception in its future. 4.2 light-years away, a red dwarf pulsates, emitting colossal energy, like the accumulated fury of billions of nuclear explosions. And orbiting this cosmic furnace is a world that could potentially become humanity's second home. The space between our planet and this distant star contains enough silent void to swallow 1 million solar systems, but it also holds enough opportunity to grant our species a future among the countless stars. The incredible journey to Proxima Centauri is not just about conquering another world. It is a guarantee that human consciousness, creativity, and capacity for love will endure long enough to seed the galaxy with life and bring meaning to it. Thank you for watching, friends. Don't forget to subscribe to the channel. See you in the next video.